about the following problem. We have a bunch of gene trees which can be discordant from each other due to incomplete linear sorting, and we have estimated a species tree. Now we want to estimate support for a species tree. And we want this to be very scalable. We want to be able to do this for very large data sets. The way people do it right now is using multi-locus bootstrapping, the traditional approach, which is a little bit slow. It's parallelizable, so it's usually doable, but it's slow because you have to bootstrap every single gene. And then there are some issues about how you interpret results that you get. We showed a few years back that if you interpret bootstrap support from multi-locus bootstrapping as, what's the chance that the branch is correct, you get some weird patterns. Okay, so how do we go about estimating supports in this particular context? So what we developed, a lot of methods that try to work on ILS are based on the fact that for multi-species coalescent model, which is what models ILS, if you start from a species tree on an unrooted species tree on 4 taxa, the probability of the gene tree that matches the species tree is always at least 1/3. And depending on the branch length, it can be higher or lower. Okay, so that should already give you an idea of how support can be computed, right? So imagine you have your 3 topologies. You have seen each of the topologies with some frequency, and these are generated through a multinomial distribution from your true parameters that you don't see. And if you are asking what's the probability that this branch is correct, that's just the probability that this parameter right there is more than 1/3, the true probability that generated your frequency. So this just becomes like tossing a die that has 3 sides multiple times and asking what's the probability that the die is biased towards one of its 3 sides. And if you then add a prior to this, you can compute a posterior probability just using the multinomial distribution. The prior that we use here is one that gives the same prior to all the 3 possible topologies, so all of them are equally probable a priori, but for branch lengths, we also need to have a way to generate a prior, and that, we use the Yule process, and it turns out that if your species tree is generated by the Yule process, your prior becomes conjugate to your likelihood, and it all works out and becomes nice and easy to compute analytically. And the posterior that you get is going to depend not just on the first topology, but also the second and the third topology, as you would expect. How does it look? If you have your quartet frequency on the x-axis, the posterior probability that you compute will look like something like this, where as you go away from 1/3 for your branch, your posterior probability goes up, as you would like it to. But also, how fast it goes up depends on how many genes you have, right? So for 20 genes, it goes up a little bit slower, but if you have 500 to 1,000 genes, 2,000 genes, it goes up really fast. So you can distinguish very short branches easily as well. So what do you do is, all of that is only if you have 4 taxa. When you have more than 4 taxa, it becomes a lot more complicated. So we make a bunch of simplifying assumptions that you may or may not like, but these are the assumptions. One of them is the locality assumption. So we assume all 4 parts are correct, so we can score all branches separately. We make another conservative approach assumption that all the quartets around the branch are so that they don't give us any extra information, so we just average their frequencies. And if you add all of these assumptions, you get something that's really fast because we can compute quartet frequencies in linear time for any branch instead of computing into the 4. At least the average can be computed in linear time. Obviously, for every one of them, you're going to need into the 4. And so this can be run on 1,000 genes and 1,000 species in a matter of minutes. We have looked at the accuracy of the posterior probabilities that we get under the conditions that completely violate all those assumptions that I mentioned. And we get support values. This is just the ROC curve. And you get support values that you